Let's look at an example problem to see why energy is useful. Suppose I'm standing 8 meters above the ground on top of the James Marshall Chapel, and I'm holding an iPhone. And I've gotten kind of tired of it, so I drop it to the ground. And I want to know how fast it's going when it reaches the ground. So how can we figure that out? I drop a 300-gram iPhone from 8 meters above the ground. How fast is it going when it hits? Well, one thing I know is I could draw a free body diagram for this cell phone. That's one of my favorite things to do to start a problem. I'd rather draw a diagram than write an equation. So what's the free body diagram look like? I know this thing is falling, so there's only one force on it. I'm going to ignore air resistance and say the force is just the mass, 0.3 kilograms, times the gravitational acceleration, which is 10 meters per second squared for our purposes. So 0.3 times 10, that is just 3 newtons. So the weight of 3 newtons is the only thing acting on this iPhone when it falls. We call that free fall, when the only force is the weight. So what can we do with that? Well, I can apply Newton's second law. It tells me that F net is equal to the mass times the acceleration. And here I see that the F net is mg, and that's equal to ma, which is pretty nice. It just tells me a is equal to g. So the acceleration will be 10 meters per second squared. That means that every second that this iPhone is falling, it'll gain 10 meters per second of speed. So I could ask, how long will that take to fall 8 meters? Well, how long would it fall in 1 second? You might be thinking that it'll fall 10 meters, but the initial speed is 0, and the final speed, that's the thing I want to know. But what I do know is that the average speed will be the average of whatever those two numbers are. So if the iPhone fell for 1 second, it would have a final speed of 10 meters after 1 second, 10 meters per second, and the average of 10 meters per second and 0 is 5 meters per second. So in that 1 second, it would fall 5 meters. So I know it'll only get to here in the first second or so. So this will take more than a second, but less than 2, because 8 meters is less than 10. So I'm already thinking, what's a reasonable answer going to be? It's going to be more than 1 second to fall, but less than 2. So now I'll check my table of kinematic equations, and I know that the height an object falls in t seconds is going to be 1/2 the acceleration times the time squared. So do I know these things? This is the height right here, 8 meters. So 8 meters is equal to 1/2. The acceleration is 10 meters per second squared. And if I'm really careful, I know that this is negative 10 meters per second squared, and it's falling a distance 8, so those are both negative. The negatives will cancel, times the time squared. So let's simplify that. I'll multiply both sides by 2, so I don't have any fractions. So 16 will equal 10t squared. So 16 over 10 equals t squared. 1.6 equals t squared. So to get rid of that squared, I'll take the square root of both sides. 1.6 square root is going to be t. What is the square root of 1.6? I will check that with my calculator, but I'm thinking, I know that 12 squared is 144, 13 squared is 169, which looks like 100 times 1.6-ish. So it's going to be something between 1.2 and 1.3. This is, it turns out, 1.27 seconds. It takes 1.27 seconds for the iPhone to fall from the top of the chapel to the ground. Now, if I gain 10 meters per second of speed every second, then after 1.2 seconds, I know my final speed will be the acceleration times the time. So that's 10 meters per second squared times 1.27 seconds. That is 12.7 meters per second. I don't think the phone's going to survive that. That is a fast speed. So that's how we solve the problem using our method using kinematics. And we applied Newton's second law to find the acceleration. So let's see a much quicker way to solve this problem, and that is using our work kinetic energy theorem, which we looked at last time. That says that the work, the net work, which is F net times how far it moves, is equal to 1/2 m v final squared minus 1/2 m v initial squared. Conveniently, what is v initial? It's 0. So this term is gone. And what is the net force? Well, I know it's the mass times g. mg is the force of gravity. And how far does it fall? 8 meters. That's equal to 1/2 m v final squared. And here you might be saying, well, why did you call it mg? You know that it's 3 newtons. Well, here's why. Because I see that there's an m on both sides of the equation. I'd rather write both of those and cancel them. Now I see that the acceleration due to gravity, which is 10, times the displacement, which is 8, and remember those are actually both negative. The displacement is downward and the acceleration is downward. That equals, my m is canceled, 1/2 v final squared. So let's multiply negative 10 times negative 8 is 80, equals 1/2 v final squared. So 160 equals v final squared. Let's check what's the square root of 160. That's v final. And that is 12.7 meters per second. So we got the same result, 12.7 meters per second, but we got it a lot faster. And that is the convenience of using energy. I don't need this intermediate step where I find the time.